This is the same matrix, the same system of equations that we were looking at in the previous video. And you'll notice here that as before, we have a pivot here and a pivot here. And so we have a pivot column here and a pivot column here. And we just said in the previous video that with that information, we know that x1, which is the variable represented in our first column, and x2 are both basic variables, and that x3 is a free variable. This is what we discussed in the previous video. What that tells us is that if we take this back into equation form, we essentially have with this the first row of this matrix, we have x1 plus 2x2 minus x3 equals 4. And we have no x1s in the second equation, plus x2 minus 2x3 equals 8. And so I might be able to eliminate the x2s if I did this using sort of pre-calculus algebra. I might be able to eliminate the x2s, I might be able to eliminate the x3s, but I don't have enough information to be able to eliminate two of the variables to figure out what the third one is. Okay, so what I end up with is an equation or a pair of equations that has too many variables for me to be able to figure out what their values are. What I can do, however, is I can write the equation for x1 and x2 in terms of x3. So let's do that. I'm going to go down here. And I'm actually going to start with the second equation here. I have x2 minus 2x3 equals 8. And so what I'm going to do is add the x3 to both sides, the x3 term. So that's going to give me x2 equals 2x3 plus 8. So now I have a way to write the variable x2 not as a value because I don't have a single numerical value for it, but I can write it as an expression in terms of the other variable or one of the other variables, right? It's the only other variable in that second equation. But because I have a different way to write x2, I can use that here as well. I can write, instead of x1 plus 2x2 minus x3, I can write, let's see, I think I'll do this here. It's kind of scratch work at this point. x1 plus 2 times, not x2, but this other way of writing x2, 2x3 plus 8 minus x3 equals 4. Simplifying, I get x1 plus 4x3 plus 16 minus x3 equals 4. Further simplifying, combining like terms, I have x1 plus 3x3, and I'm going to subtract 16 from both sides, so I get negative 12 on the right-hand side. And now I'm also going to subtract the 3x3 from both sides, so I get x1 equals negative 3x3 minus 12. And I'll just jot that down over here with the other one. I have x2 written in terms of x3, but now I also have x1 written in terms of x3. I have x1 is equal to negative 3x3 minus 12. All right, so I have a way now, I would argue, of writing a triple x1, x2, x3 for this system, but I don't have single numerical values. What I do have is, let's see here, is I have x1, which I know to be negative 3, x3 minus 12. I have x2, which I know to be 2, x3 plus 8, and I have x3. Now remember that x3 was the one that we were saying was a free variable because it's not associated with a pivot column. But now I can explain a little bit better, I think, why we use that term for this. Because x1 depends on x3 to be defined, right? And so does x2. That both of those variables require a value for x3, but x3 doesn't depend on anything but itself. It's free to be any value. And once we have a value for x3, we can also define values for x1 and x2. So for example, in the matrix that we're playing around with up here, I can say, let's let x3 equal 0. And when x3 is 0, I get 0 for x3, obviously. I get 0 minus 12 for x1, and I get 0 plus 8 for x2. So when x3 is 0, negative 12, 8, 0 is a point in the system that solves the system. It satisfies both of the equations in the system. So that's essentially a solution to the system. Let's take a look, though, at another one. x3 equals 2. I'm kind of pulling these out rather randomly. In fact, let's make it negative 2. When x3 is 2, negative 2, x3 is going to be negative 2. But x1, which is defined in part by x3, is going to be negative 3 times negative 2, that's 6. 6 minus 12 is negative 6, so my x1 is going to be negative 6. And x2, which is also defined in part by x3, is going to be 2 times negative 2, which is negative 4. Negative 4 plus 8 is 4. So I have another solution. I have negative 6, 4, negative 2. And this is the case because we have a free variable. There are an infinite number of solutions to this system of equations. The form that we have up here in the sort of triple coordinates here, negative 3x sub 3 minus 12, comma 2x sub 3 plus 8, comma x sub 3. This is what we call parametric form for the solution to a system of equations or the solution to a matrix with a free variable, right? x3 is free to be anything that it wants to be, and then x1 and x2 are defined by whichever value you pick. And in fact, you can pick multiple values, and that's the benefit and also the downside of having a free variable, right? What this means is that you have multiple solutions, and that therefore that this is a system that does not have a single point that answers it, that satisfies all of the equations. The title of this subsection is Parametric Form of a Solution, and this has kind of been a long-winded explanation of how we get to that. But for the record, ultimately, this is the answer to the question, what does it mean to be in parametric form? Specifically, what does it mean for the solution to a system of equations to be in parametric form? Notice that in order for that to happen, one of the variables has to be a free variable. The free variable is effectively the parameter on which the other variables are defined.